Next we have exercise 9. In this one we have the set A of all integers from 0 to 12, and on A, two relations have been defined. The first one consists of ordered pairs A comma B. A and B of course are coming from A, they are elements of A, such that the absolute value of A minus B is divisible by 4. And the second one consists of such ordered pairs again of elements coming from A where the coordinates are equal. We have to prove that each relation is an equivalence relation, and we also have to find the set of all elements related to the element 1 of this set. That means in each case we have to find the equivalence class of 1. So let us see the solution. In part 1, we immediately simplify the definition of the relation R. We can actually get rid of absolute value. That is because for any two integers, the absolute value of A minus B is divisible by 4 if and only if the ordinary difference A minus B is divisible by 4. And that is why instead of the original definition of R, we can use this slightly different definition of R as well. Although we are getting exactly the same ordered pairs here also as we have in the original R. That is, it consists of those ordered pairs of elements of our set A such that A minus B is divisible by 4. So now we do not have to bother about the absolute value. Now with this new characterization of the relation R, we are going to proceed. So let us take any element A in A first. A minus A is 0, which of course is divisible by 4, and that is why A comma A belongs to R using this new definition. Thus R is reflexive because this is being true for any A in A, for all A belonging to A. Next, let any element A comma B, let us consider such an element in R. Then A minus B is divisible by 4, but then its negative is also divisible by 4, which is B minus A. So that way B comma A also belongs to R, which makes R symmetric. Next, let us see transitivity, which is where actually we are going to need this simplification. Let's see how it can be obtained. So next, for transitivity, we take these two ordered pairs in R, A comma B and B comma C. By the definition of R, or rather by our characterization of R, this means that A minus B and B minus C are both divisible by 4, but then their sum would also be divisible by 4, that is this, which however is A minus C. Because A minus C is divisible by 4, by our characterization of R, A comma C will belong to R. But that means R is transitive. So being reflexive, symmetric and transitive, R is thus an equivalence relation. Next, we have to find those elements in our set A which are related to the element 1, or in other words, we have to find the equivalence class of 1. That's the next thing. So let us name that set B. Let B be the set of those elements of A that are related to 1. Now, what type of elements will be related to 1? Say that element is X. That means the absolute value of X minus 1 should be divisible by 4, or by our characterization of R, the ordinary X minus 1 should be divisible by 4. That means X minus 1 should be of the form 4n for some integer n, or X should be of this form 4n plus 1 for some integer n. Now the original set of course consists of all these integers. Among these integers, what are those that are of this form 4n plus 1? Let us put some values of n and see. If you put a negative value of n, you are going to get a negative integer. We do not have negative integers here. What do you get if you put n equal to 0? You get 1. So that's why we have the element 1 in B. If you put n equal to 1, then you get 4 plus 1, so that way you get 5. If you put n equal to 2, you get 9. So that way you get 9. There are other integers of this form as well. But if you put n equal to 3, you are getting 13. So you go outside this set. So these are the only elements in this set that are related to 1. So this is the set. Next, let us see part 2, which is actually very easy. It's almost trivial. Okay, so this is the solution. Everything about it is obvious and trivial. Let us take any element A in A. Since A is equal to itself, by the definition of our relation, A comma A belongs to R. So R is reflexive. Next, let A comma B be an ordered pair in R. Then by the definition of R, A is equal to B, but that implies B is equal to A, so B comma A belongs to R. So that way R becomes symmetric. Next, let us take these two ordered pairs in R, A comma B and B comma C. Then again, by the definition of R, that means A is equal to B and B is equal to C. But that implies that A is equal to C, and that's why A comma C belongs to R. So R is transitive. Being reflexive, symmetric and transitive, R is an equivalence relation. Instead of writing like this, I'm talking about writing an exam. Okay. In an exam, you can write one more line. Instead of straight away from transitivity writing that R is an equivalence relation, you can write one more line that since, or you can enlarge this line, since R is reflexive, symmetric and transitive, that's why it's an equivalence relation. That is because our exam papers are supposed to be like essays. We do not like concise, to the point answer. We like to unnecessarily expand things. That is why it may get you good marks. But anyway, next we come to the set of those elements in A which are related to 1. Looking at the definition of R, in this case, that set of course consists of just 1, nothing else. Let us see the next exercise next. In this next one, 10th one, we are seeking some examples of relations which satisfy some properties. There are some parts. The first part asks us for a relation that is symmetric but neither reflexive nor transitive. So let's see the solution. So one easy example is this. We considered the set consisting of 1 and 2, and on that, well, you can give it a name also, you can call it A. And on that, consider the relation consisting of these two ordered pairs, 1, 2 and 2, 1. Is it symmetric? Yes. Is it reflexive? No, because 1, 1 is not there, 2, 2 is not there. Is it transitive? No, again no, because you have 1, 2 and 2, 1, but 1, 1 is not there. Actually, the solution doesn't end here. You have to write these extra things. You have to justify why this relation is symmetric but neither reflexive nor transitive. That part I am leaving to you. Okay, so I will just simply, in the subsequent parts also, I will just give the example and the explanation is left to you. So let us next see part 2. So this is part 2. Here we want a relation that is only transitive. It's neither reflexive nor symmetric. And this time we take a slightly larger set consisting of 1, 2 and 3. And the relation on that set is this. It consists of the ordered pairs 1, 2, 2, 3 and 1, 3. Again, let me just tell you a little about how this relation satisfies these properties. It is transitive. You note that you have 1, 2 and 2, 3. So transitivity demands that you have 1, 3, which you really have here. Any other combination of ordered pairs, the combination should be like this: A, B and B, C. If you start with 1, 2, then you should have 2, something. And the only element of that type is this ordered pair. So that we have verified. If you start with 2 comma 3, then you do not have 3 comma something, so that does not cause any problem to transitivity. If you start with 1 comma 3, again you do not have 3 comma something, so this also does not cause any problem to transitivity, and that is why it is transitive. It's not reflexive, you understand why. For example, you have the element 1 in the set, but 1 comma 1 is absent here. Okay, it's not present. It's also not symmetric. You have 1 comma 2, but you do not have 2 comma 1. So you have to nicely write these things. So that is part 2. Next, let us see part 3. In part 3, we want a relation that is reflexive and symmetric. This time it has to satisfy these two, but not transitive. So we have thought of this relation on, again, that set 1 comma 2 comma 3. So it has the ordered pairs 1, 2. Let me not say comma because it takes some time to say 1, 2, 2, 1, 2, 3, 3, 2, 1, 1, 2, 2 and 3, 3. So you can immediately see that because of the presence of these ordered pairs 1, 1, 2, 2 and 3, 3, the relation is reflexive. Symmetry also is equally easy to see. You have 1, 2, you also have 2, 1. You have 2, 3 and you also have 3, 2. And these elements, of course, if you swap the coordinates, you get those elements themselves which are already there. Why is it not transitive? That's because you have 1, 2 and 2, 3, but 1, 3 is not there. Okay, so you write these things. So that is part 3. Next, part 4. In part 4, we want a relation that is reflexive and transitive this time, but not symmetric. So on that same set, this time we have taken this relation consisting of the ordered pairs 1, 2, 2, 3, 1, 3, 1, 1, 2, 2 and 3, 3. So presence of 1, 1, 2, 2 and 3, 3 immediately tells us that the relation is reflexive. Okay, so reflexivity is there. And you can also verify transitivity by considering those combinations. Let me give you one example. You have 1, 2 and 2, 3. So you have 1, 3, which in the previous relation you did not have. And other possible combinations will also none of them will cause any problem to transitivity. So it is transitive, but it's not symmetric. For example, you have 1, 3, but there is no 3, 1. So that is part 4. And I think there is a part 5 also. So let us next see that. In part 5, we want a relation that is this time symmetric and transitive but not reflexive. It is this other two, just it's not reflexive. So on that same set, this time we have taken this relation consisting of the ordered pairs 1, 1, 2, 2, 1, 2 and 2, 1. So you can immediately see that it is symmetric. You have 1, 2, you have 2, 1 and the others, of course, each one has the same coordinates. It is also transitive, which you can check. Okay, for example, you have 1, 2 and 2, 1, so you have 1, 1. If you come from that side, 2, 1 and 1, 2, you have 2, 2. Okay. You can actually consider, you should consider the other possibilities as well. For example, 1, 1, 1, 2 are there, so 1, 2 should be there, which already is there. So this is symmetric. Transitive. So it is symmetric and transitive, but it's not reflexive because you do not have 3, 3. So that concludes this solution. Let us see the next one. This next 11th one is about geometry. It's geometric in nature. Here the set of points or the set of elements on which we have some relation is the set of all points in a plane, in an infinite plane. And this is the relation. So the elements in the relation will be ordered pairs of points coming from the plane. Two such points P and Q are defined to be related if they are equidistant from the origin, if they are at the same distance from the origin. If you simply have a plane from your ordinary geometry, that actually does not automatically come with an origin. An origin appears only when you have drawn an x-axis and a y-axis in the plane. So because origin has been mentioned, so it's assumed that there is some coordinate system. We have to prove that this R is an equivalence relation, and additionally we have to show that the set of all points related to some point P which is not the origin is the circle passing through P, passing through that point, and which has the origin as its center. So let's see the solution. Showing that the relation is an equivalence relation here also, it's almost trivial. So what you do, you take any point P in the plane. P and P are of course equidistant from the origin because they are the same point, and that is why P comma P belongs to R, making R reflexive. Next you consider an ordered pair P comma Q in R. This means that P and Q are equidistant from the origin. Their distances from the origin are same. But then obviously Q and P are also equidistant from the origin, and that is why Q comma P also belongs to R. So this makes R symmetric. Next we have transitivity. So for transitivity we have chosen these two ordered pairs in R, P comma Q and Q comma S. See, there will be a tendency of writing P comma Q and Q comma R. Do not do that, okay? The letter R already denotes the relation, so you cannot use it elsewhere. So that's why we have chosen S. You can use any other letter as well. But then P and Q are equidistant from the origin, and so are Q and S. That means the distances of P and Q from the origin are same, and the distances of Q and S from the origin are also same. But then obviously the distance of P from the origin should be equal to the distance of S from the origin. So P and S will also be equidistant from the origin, and that is why P comma S belongs to R. So this makes R transitive. So being reflexive, symmetric and transitive, R is an equivalence relation. And then we have that other part also. For that we have named the circle which passes through some point P which is not equal to the origin, and which has the origin as its center C. Okay, so we are naming this circle C. Now we have to prove that C is precisely the set of those points that are related to P. Let's see how. So we have started our argument by considering any point Q in C, and for our own benefit, for our understanding, we have drawn a figure also. I think it's a good idea to include this figure in your solution if you are writing this in an exam. So you have P here. P need not lie in the first quadrant, it can lie anywhere. The only condition is that P is not the origin. So I have just simply drawn P here. So the circle that passes through P and has the origin as its center is this circle, which is C. Us choosing Q in C means that Q is the point on C, somewhere, say here. Then what? Then obviously P and Q are equidistant from the origin. Why? Well, that is because they lie on that circle which has the origin as its center. So obviously these two distances will be equal. They are equal to the radius of the circle. And that is why, by the definition of our relation R, P is related to Q. P comma Q belongs to R. So we see that any point Q on C is related to this point P by our relation. Are these the only points, or shall we have some other points in the plane also related to P? So next we have to show that that's not the case. So for that, let us choose any point S in the plane that is related to P. Then by the definition of R, P and S are equidistant from the origin. However, in that case, S is bound to lie on C. Why? Because C is the circle that passes through P and whose center is the origin. So, if some point is at this distance, then it cannot lie outside C, it has to lie on the circle. So, that way S has to be a point in C. So, we have proved that C is precisely the set of those points which are related to P. So, you have to write one more line. So, then the solution will be over. And finally, let us see the next one also. Next, we have exercise 12, and this is also geometric in nature. However, here the set of objects is not a set of points, but rather the set of all triangles in a plane. So, you fix a plane, and in that plane you consider all possible triangles that you can draw on the plane. So, on that set we have a relation. This relation relates to triangles T1 and T2 if T1 is similar to T2. Recall the definition of similarity. If you can put the internal angles of two triangles in a correspondence. So, that is say you have two triangles ABC and DEF. Say you make the internal angle A correspond to the angle D, B to C, E to F, like that, so that these corresponding angles are equal. If this is possible, then the two triangles are similar. And you also know that similar triangles have sides in the same ratio. So, you have these facts from elementary Euclidean geometry. So, then you have to prove that this relation is an equivalence relation on the set of all triangles in a plane, which actually proceeds exactly like how we did the other exercises. So, this part I am leaving to you, but there is a second part also. Three triangles have been considered, all of them are right angled triangles. T1, which has these side lengths 3, 4 and 5. T2 is another triangle with side lengths 5, 12 and 13, and T3 has side lengths 6, 8 and 10. From this we have to decide which of these three are related to one another. So, we are going to solve this second part. So, let us see the solution. So, we start the solution like this. To prove that the relation R is an equivalence relation, proceed as we did in the previous solutions. And now for the second part, we note this. The sides of the third triangle have lengths 6, 8 and 10, whereas the sides of the first triangle have lengths 3, 4 and 5. And you can see that 6 divided by 3 equals 8 over 4, which equals 10 over 5. So, that is why T1 and T3 are similar. The fact that if you have two similar triangles, then their corresponding sides are in the same ratio. It works the other way around also. If the corresponding sides are in the same ratio, then the triangles have to be similar. Recall this also from ordinary geometry. And that is why T1 and T3 are similar. But that is not the case with the side lengths of T2. Okay, so the sides of T2 are not in the same ratio as the sides of T1 or T3. So, T2 is not similar to T1 or T3, and as such, T2 is not related to T1 and T3, just like T1 and T3 are related, T2 is not. So, you write this final part and complete the solution. So, that will be all for today. See you tomorrow with a new upload. Until then, this is me, Lucifer from a mathematical group. Have a nice day.